Can you hear me? Hello? Hello?
Yes, sir.
Can you see the screen?
Yes, sir.
Yes, sir.
Okay, let me start. Well, I taught to compactness in the last semester, so that those things I won't repeat. Those things I will assume you know, but I will teach more. Okay. First of all, compactness, I wrote, again you should read that. It is everywhere in math. Whether you do applied math, pure math, everywhere it is here. Okay. So that, first of all, compactness, you have X is said. First, now you don't need to talk about topology and the cover. Suppose you have some I, big I is an index set, each AI is a subset of X. Then if you have this, then this is called a cover. Cover of X. Now you can analyze this if you take a B subset of X and suppose you have this. Instead of whole X, you are taking a subset. Then this is called a cover of, is called a, then this one is called the cover of P. So for the definition of cover, you don't need any topology, but topology will come when I talk about open cover. Now suppose you have this X star, and suppose each AI is open. That means each AI belongs to top. Then this is called open cover of P. Okay. Now the question is, this is fine. This is definition. It's called an open cover of P. Now, what is compactness? I mentioned one place that compactness is a generalization, topological generalization. Compactness is sort of topological generalization. Of finiteness. More precisely of finite sets. More precisely finite sets. I think if you read the note again carefully on that, it will be clear to you. But so that so Now the compactness definition again I am telling you. So suppose you have x tau, definition 5.1, x tau is a subset of x. I have taken E. ठीक है, E ले लो. Is subset of x, and this is a collection of sets. Okay, that is the cover I have given. And suppose this is, that means that is each member of G, sorry, is a subset of X. Okay, right? And suppose you have this. That means this is an open covered of E, and moreover, suppose that what I've said that I'm repeating. And suppose each member of G is actually this. That means each member of G is actually open. Then this is called an open cover of. See, topological space means cover. First, you know what is cover. Its union of those sets will have to cover the given set E. And open cover means the members of open. That way, similarly, you can define closed cover if each member is closed. Okay, but not mixed up. Okay, so that now if every open cover has a finite subcover, that I said. So that E is called compact. In X tau, if every open cover of E, open cover of E has basically in X tau. Open sets, this means open sets are coming from this tau, has a finite subcover. What does it mean? Say, usually we take this. That is, there exists one UN in U such that look, this number n will depend on you. If you change to another open cover, then you may not have the same n, but it will be always finite. So you have it. So it has a finite subcover. That's the thing. Because many things we can do, even if we do not have this, but if we have this compactness, we can do that. Okay. Now the thing is, this is not in this note. So listen to me carefully. I do not think you did well in the minor one exam. I could see some of your faces on that. But the question, the answers you'll be getting when you get the paper and that everything you'll get, and then you realize that answers were not difficult. Okay, only thing Maga won't help. You need to attend the classes regularly, and it's not enough to go through the notes of that. You'll have to think. Okay. Now, what I'm going to say that definition, I want to talk about thing so that this is not in the note. I avoided last semester, but this semester I think I should teach you. So look, even when if you take E equal to X, then X is compact if every open cover f X, as a finite subcover. In that case, since everything is coming from this, it will be this. Okay, if E equal to X, because everything is a subset of X. Now the suppose, now think of this. Compactness is a topological concept, so that look, this E, I have given compactness of E, I have given with respect to X tau. But I can see, of course, you assume E is non-empty because empty set by definition is compact. So you can assume E is non-empty. Now look, E tau E. This is itself a topological space. So I can think of its own compactness with respect to tau y. So I can think of compactness of E with respect to tau. Okay, right. That means here the open sets will come from here. Okay, so I can think of compactness of in two ways, with respect to this and with respect to this with the cover. But are they different? That the question is, because it's a very vital in math, in analysis and topology. No, they are not different. So that the result I'm saying is I am leaving it an exercise. I'm saying result. Just look that. Let X tau be a topological space and is a non-empty subset of X. Then is compact in X tau if and only if this thing, we say that the subspace topology. What is the advantage? It has got a big advantage. That means, look, if I had when X, Y, and suppose you have, then you could have go to subspace topology here, or it could go by steps. Like on E you have that I taught you already. On E you have two topologies. One is straight tau E, other one is tau Y first, and then you are taking this. And these two are equal actually. It doesn't matter whether it goes by step or it goes direct in that. Okay, so that now look, if you have this and together with this, that means E will be compact. It will mean that E is compact in Y if and only if, that is Y tau Y. If and only if E is compact in X tau. Because ultimately both will be because of this, it will be the compactness of this. Okay, so it's because of that. That is the first corollary that. So this means what? It doesn't matter where it is sitting through. So it will be, if it is compact itself, it will be compact with respect to any superspace, any topological space which is containing it as a subspace. That means compactness is sort of absolute concept. It doesn't depend on the relative topology. Compactness is an absolute concept. Whereas you see the difference. Closed is not, because it may be closed here, it may not be closed there. That you have seen that. Closed thing, so closed is much weaker. Closed is not that. Okay, that you have seen. In the R you can see that. Okay. R you see that if you take this. You take whatever. Okay. Now you see that. What is here? This is closed here. This is not closed here. This is not closed here. Okay, right? You can go other way that. So you can find something that always example from here. So this is closed here, but it is not closed here. It is not closed here. Similarly, I can find a set which subset which will be closed here but not closed here. Okay, that you can think of that. So there is a difference between so closedness is not an absolute concept. Sorry. But I'm saying think about it. It makes a big difference. Okay. You take some subset and that. You think about it. Look, E itself is closed. In itself is closed in eta V. Okay. But it may not be closed here. Like here. The 0, 1. If I take, yes, open interval. This is closed in here itself, the big whole set. But this is not closed here. This is not closed here. So E may not be closed in Y or X. Okay, but for compactness, it won't happen. So compactness is an absolute concept. That's why it has got the advantage. Okay, and now the thing is that I have taught last semester. It is the proof is there. You will see that. Theorem proposition 5.2. In the note, you see the page 155. If it is a Hausdorff space, x tau is Hausdorff T2. And every compact subset is closed. That's a good thing. So that means if you take collection of closed sets, collection of compact subset is the subset of that family of closed sets. But if it's not Hausdorff, then it need not be true. That's the example. I have given that. The example I said you should look at Aliprantis and you can have your own thing. Think of that. God. Yes. Now you should solve the problem that Aliprantis Barkinsa. Problem number 21. Page 65. Let me see that. What is there? Yes. So make sure that you solve this problem. This is exercise. Read that carefully. Okay. This is very important. Okay. Right. That if it is not house drop, then it need not be closed. In fact, he has given that. You can have a simpler example. Look, if you take x tau, tau is cofinite topology and x is infinite. It is not Hausdorff. Is it Hausdorff? Or you can take uncountable infinite. X minus. Yeah, I think that. Where the open sets here? X, phi, u, such that x minus u is finite. Okay, that is closed, so these are open. And closed sets what? Ax, phi, and all finite subsets of x. Okay, these are closed sets. Okay, right? And is it house drop? If you take two open sets, UV then X look, of course I can take U not equal to X not equal to V also, because I want disjoint to proper open sets. So take this is finite, this is finite. Okay, but this is if you have this is disjoint, then this will be infinite. So this is not house draw. Not what are the compact sets? Compact subsets of well. So we take, let's see that what would be the compact subsets of X. Okay. Well, take a subset of X, of course non-empty. Okay. Take open cover I open in X. Okay. Now choose a point X belongs to A. So there exists I belongs to I index set such that X belongs to AI. Sorry, UI. Okay, right. Now look, just see that if UI is X, then nothing to prove. Then I will just pick up X. That will be a finite subcover. If UI is X, nothing to do. Then I will take simply UI is the X, and that will cover whole leg. and that will be a finite subcover. So you choose uy not equal to x. That means x minus uy is finite. This is the argument, kind of argument I have given. X minus ui is finite. So outside ui, only finitely many points of a can be there because x minus ui is finite. Okay. So suppose you have x1, x2, xk is outside this, belongs to this. Can have it only finitely, suppose. So for each of them you pick up one member which contains this, and together you add with this, it will give you a finite subcover. That means what you are getting? That means any subset is compact. Got it? So any subset is compact, but any subset is not closed. So a compact subset need not be closed. Okay. See, well, I give the example here. So that cofinite topology with infinite, that is one another example that compact subset need not be closed. Compact subset need not be closed. Okay. Right. Here, just lest I forget, I'm just giving an example. Suppose R, you have the usual topology. And by argument, you know every finite subset is compact in any topological space. Now on this you give another topology. What is this topology? Here you give the topology tau. Sorry. Compact here. Look, every finite set is compact here. So it will have for all finite sets, all complement of finite sets. So that means it will be bigger than cofinite topology. So that, check that one. This is a co-compact. It is called the co-compact topology. Complement of compact subsets we are taking. Co-compact topology. Check tau is the topology on R. 2. Tau is strictly finite than cofinite topology. 3. Find out cofinite topology. I found out the compact subset. Find out that we characterize. Find out all compact subsets in this. This is your exercise. Okay. This is called co-compact topology. Co-compact topology. This is very important for counter examples. Okay. Make sure that you do it. The next exam I may give something where you need to use this. Okay. Now look, the proof of theorem 5.2. Okay. Where I used compactness. I said you have a topological space Hausdorff. If it is not Hausdorff, it need not be true. Hausdorff. Empty set is always closed, so don't worry about. So the non-empty K, non-empty. This is compact. This is given. And to show This is closed in extra. Okay. So look how I proved. I'm just briefly telling you that how I proved that. Okay. I showed basically if you have a point outside K, then it is not a closure point. That means K must contain all its closure points. Okay. So it has to be closed. Look, K bar, if that means the collection of closure points. So if it is this, that means implies K equal to K bar. But K bar is always closed. That means K is closed. So what I'm saying here that no closure point, if a point lies outside K, that is not a closure point of K. And then how I used Hausdorff. Okay, so take any X outside K and keep it fixed. Now you take this pair. X, oh, I have taken here A. Okay, fine. So that you don't get confused with that. So take A. Okay, so that you have A and choose any X, this pair. X in K. You are choosing any point in K, but keeping it fixed. Now, A is outside K, X is in K, so they are different, distinct. So by Hausdorffness, there exist open sets Ux because A is fixed. Only Ax will be changing. That should keep track of the sets. I'm giving a level subscript. Okay, so that you have there exist A belongs to Ux, X belongs to Vx, Ux intersection Vx is empty. Ux Vx are open. Okay, that you are getting because you are using the fact this Hausdorff. Okay, now look, A is fixed. Now I'm repeating this is for all X. That means I will get this will be is an open cover of K. So be careful about it. This is an open cover of K. Then what I did this. I took Vx is an open cover of K. Since K is compact, look, I'm repeating. Since K is compact, it is of a finite subcover. So, but index set itself is K. So that is there exists x1, x2, xn in K such that this okay, right? Now corresponding to each x vxi I have uxi. Now you take u equal to v equal to this. And u equal to intersection. Look, A, don't forget about this. A belongs to each uxi. So A belongs to U. Look, this is a finite intersection of open sets. U belongs to tau. And then you show that because of that property. V intersection U is empty. That means V, but K is a subset of V, so that but U is the neighborhood of A which is not intersecting K, so that A doesn't belong to K bar. Right? So any point outside, this is not a closure point. But where actually used compactness in that. Look, here, just see that. If my argument now think of that. If I didn't use any compactness, still I will have, this is true. Okay, look, this is arbitrary union open sets. So even if you call it V prime, suppose, so this is open in X. But correspondingly, same argument disjoint, I'll have to take U prime equal to, I'll have to take this. Still, I will have this. Only problem is this, look, here it is arbitrary intersection open sets. C prime need not be open. Okay, need not be open. And that is where I used compactness, because I reduced it to a finite subcollection so that I have finite here, so I can claim this is open. So that's the exactly how we are transforming compactness into finiteness. I needed to hold up a finite subcollection so that in here also I have finite subcollection. So that's why it will be open. So that's the thing that you'll have to see the proof. Okay, right? And this thing. And I remark, I say, now I want to prove that this is, I have not given the result. This result I have to, because what the next result I want to give you, this result. This theorem. Let X tau be a housed of space okay, and to non-empty disjoint compact sets, compact subsets of X. Then there exist open sets UV in X such that you have this K subset of U, H subset of V, U intersection V is empty. That means two disjoint compact subsets can be separated by open sets. Okay. The thing is that to prove this, we proved that theorem 5.2. This is what proof is not now is not difficult, because here to prove this we use this and its technique as well. Look, there actually in the proof I said, actually I proved something stronger conditions. Okay, what I proved actually. Okay, I proved, look at the proof that, okay. Look what I proved there, when if K is compact, in theorem 5, I proved something more than I required, and X doesn't belong to K, because this is required, what I have got there. Then there exist open sets U and V in X such that, I don't know which way I used U and V on that, so don't bother about it. Look at this thing, such that K subset of U Actually, I think I got other way. Okay. If you want, I can take that, but don't worry about. X belongs to V, and U intersection V is empty. There U I take here, I think, and V I take here. Okay. So actually I proved this thing. K is compact, X doesn't belong to V, then there exists open set such that. So actually to prove this we use this result and the technique. Okay. So let us see. So that again we'll use that compactness value. Look, both are given compact. So one kind of compactness, one for this, I will use the previous theorem. Okay. Now look. So take X belongs to H. Then consider this pair. That means X doesn't belong to K. So by the proof of theorem 5.2, there exist open sets. Since it is I will be changing X so that you should have Ux Vx. Okay, there exists open set Ux Vx in X such that this is not in the note. Okay, but you can find it in Willard. So this is what you are getting. K subset of Ux, X belongs to Vx, and by the proof, not exactly the statement. Okay, now you have got this K subset of Ux. Now look, you got X belongs to H. For X belongs to H, you got K subset of Ux and X belongs to Vx. Now you are doing for each X of this. So that look, Vx, X belongs to H is an open cover of H. But H is given to be compact. So there exist finite indices. The index it is H itself. In H such that H is now look the technique. But each time I have this. Right? So if you take U equal to, then K is contained in this. And you call it V. Then H is contained in V, K is contained in U. Look, V is open. Finite in an open set. The finite intersection open set is open. And U intersection V is empty. Why? Well, take this. U is this. You better take this. V. U intersection this is union no T is a subset of UXI and with UXI it is empty, so this is empty. U is a subset of UXI and UXI VXI is empty set, so it is a union of empty sets. So you get this. This is this. So you are using the technique, we are using that theorem, that is the proof of that theorem. Okay, so that the theorem 5.2, make sure that you read the technique carefully. That I said remark. It's actually where you use the compactness. Okay, and then you prove this result. Now look, that I am not going to prove, it is here. Every closed subset of a compact set is compact. That is theorem 5.3. F is closed subset of a compact set is compact. So proposition 5.3. Why I need that? So X tau, you have a topological space, and you have this. K is compact in X. F is, don't forget, not closed in K. But if you Hausdorff space, it won't make a difference. You can see that. Closed in X. Then this is implied F is also compact. So particularly if X is compact, that means if you take K equal to X, then closed subset of a compact set is compact. Now look, in the proposed theorem I proved, if you have X tau itself, compact Hausdorff space. You'll see that where I'm using Hausdorff. Now take two closed subsets. Of course, you can take non-empty. Empty set, you won't have to do anything. Closed. Now look, by this result, closed subset of a compact set is they are compact. I don't know where you require. That is closed subset of a compact set is compact. Now look, the previous result that what I proved, I used Hausdorff because I was using the proof of theorem 5.2. So Hausdorff is required. Now if you have Hausdorff, then by the theorem I proved, these two compact sets can be separated strongly by open sets. I am using Hausdorff because in theorem 5.2 I used Hausdorff. U intersection V is empty, UV open. That is what I have got. I started with two disjoint closed sets. Of course, you take this. They are compact, so two disjoint compact sets. So I get this. That means any two disjoint closed sets can be separated by open sets, which is precisely the definition of normal space. So that means what I proved, a compact Hausdorff space is always normal. It's a link. So that I proved this theorem. This is a good theorem. Make sure that you understand the proof. A compact if this is not Hausdorff, it is required. That is a compact space. Find an example. Say non-Hausdorff compact space which is not normal. That is your job. You'll do that. You can ask Saurabh, but better you need to think. You should do in undergraduate. You have done a lot of math, but mostly non-thinking math. That you have done. because mathematics you have equated with computation. Here I should tell you some funny story. Now in computer science, people say they do computational mathematics. In fact, computation is not mathematics. What is called thinking mathematics is mathematics. In fact, it is before Second World War. Turing, you will see that some other Turing machine, some other before Second World War, already computation was coming in a big way. So then mathematicians themselves, they realized if this trend continues, then ultimately computation will overshadow mathematics. Everywhere it will be only computation. So that it is the mathematicians who founded computer science to separate computation from mathematics, to save mathematics. Okay, so the founders of computer science, they're all mathematicians, nobody else. Okay, and they did intention to save mathematics, In fact, founders of computer science, they're all abstract mathematicians, so-called theoretical mathematicians, not so anything like applied mathematicians. Okay, so Turing machine, you can think of that. Turing himself was an abstract mathematician. So that's why I'm saying computation, because they realized computation is becoming a big part of mathematics, and they wanted to avoid it to being a part of mathematics. So that's why they separated computation from mathematics. But until now, what you have learned in the name of mathematics, mostly, I'm not saying all of you, that is computation. You have not learned mathematics much. That's why you are having the problem. Okay, mathematics, you'll have to think. If you believe in God, I don't believe in God. If you believe in God, and if your God has given you thinking power, make sure you use your think power. Brain, I am telling you, is a weapon which doesn't get blunt with more use. If you use it more, it gets sharper. If you use it more, it gets sharper. Okay, it doesn't get blunt. So that's why you should use your brain. Okay, wherever, in some basic things, whatever you should use your brain. Okay, so that, fine. So that make sure that you read theorem 5.2, its proof. You require, and then you prove this. Okay. Now, two more concepts I will do that, and then I will teach you tomorrow. Let me, what is that, those concepts? Here, concept is Lindelof. This is not in your note. And countably compact. Look, what is compactness? E subset of X is called compact if every open cover of E has a finite subcover. So first thing, countably compact will come later because it's finite. If I do a generalize, suppose instead of finite, I take countable subcover. That means countable means countably infinite, finite, or countably infinite. That is countable. Suppose I replace it by countable. Still, it's a good property. It may not be as strong as compactness. Suppose you have it, then this is called Lindelof. Lindelof was another topologist, one of the founders of topology. So that, let me give the definition. Let extra be a topological space and D subset of X. Then is called Lindelof if every open cover of phi has a countable subcover. Countably compact I will come later on. I want to do only Lindelof. Countable subcover. Look, only compactness you are substituting this thing. Countable subcover. Immediate two observations of that every open cover. Again, you can see that this is an absolute concept. Okay. So that Lindelof, what I commented with respect to compactness, it is also there. It's an absolute concept. Second thing, every compact space is Lindelof. Okay. In fact, any compact subset, you can do it more generally. If X tau is a topological space, then any compact subset of X is Lindelof. But converse will not be true. But a Lindelof set subset, but a Lindelof, this is two dot, it's called umlaut. ये क्या हुआ है इधर Lindelof subset did not be compact. In fact, by Heinbudel theorem, we know that this is itself is not compact because it is not bounded. But this is Lindelof. How to prove that? But it is Lindelof. Okay. In order to prove it, I will give proof tomorrow on that. But I am giving the result. First result is this. You can think of that. We have seen every second countable space is separable. So every second countable space is Lindelof. Okay, that proof is not difficult. You can think of that. Otherwise, I will give it tomorrow. Every second countable space is Lindelof, but a Lindelof space need not be second countable. For R it will work, but if you take Surgeon-Fay line with lower limit topology, in Willard he has used this notation. Surgeon-Fay line. The Surgeon-Fay line, you already have seen that this is not second countable. Surgeon-Fay line, this means RL is Lindelof, but not second count. So you need to only prove Lindelof, not second count. Well, so this proof too, I will prove it tomorrow. Now the thing is, another result I will prove. In metric space, we have proved that second countable is same as separability. In fact, for a metric space, Second countability same as Lindelof. So that means for a metric space, second countable, Lindelof, separable, they are all same. So let me write this result. For a metric space, xt, the following are equivalent. Xt, it means topology generated by D, is second countable, xt is Lindelof, C, xt is separable. I have proved equivalence of A and C, but now I'll prove equivalence of A and B. But actually I'll go this way. A implies B, B implies C, C implies A, like that. This is separable. So this for a metric space, that's why metric space is a very nice property. Only when if you have non-metric space, non-metric space, then it's a problem. Like Sargent-Frey line. Sargent-Frey line is not metric because this is not second countable. But this will be Lindelof. That you should check. Okay, that's an exercise. The Sargent-Frey, it is given in monkeys, the proof. Proof is bit tricky. I won't ask you in the exam, but you should read the proof to see that if you can understand the proof. Proof is not difficult, but a bit tedious. Okay, so that tomorrow I'll prove this result about Lindelof. Then I'll come to countably compact. So see you tomorrow. Okay, bye.
ओ भाई ये मतलब